Welcome to a journey into the realm of graph theory with a focus on the four-color theorem. This theorem, a beacon in the field of mathematics, has intrigued and challenged mathematicians for over a century. It states that given any separation of a plane into contiguous regions, producing a figure known as a map, no more than 4 colors are required to color the regions of the map such that no two adjacent regions have the same color. Now imagine the plane as an existential space, the regions as non-intersecting shapes, and the colors as distinguishing semantics. This is the essence of our journey today as we delve into the four-color theorem using the framework of existential computation, XCR, and semantic computation, ESCR. In the world of XCR and ESCR, a color represents a semantic marker, distinguishing filled areas from unfilled ones. The number of colors required in different scenarios is determined through the analysis of existential semantics and semantic range. In a plane where no lines exist, one color suffices to fill the entire plane. The introduction of a single line necessitates 2 colors, splitting the plane into 2 regions. With 2 lines, the plane is divided into 4 regions, each requiring a unique color for differentiation. Yet this differentiation happens within a specific semantic range, defined by the coordinates of the lines. With 3 lines, more regions are created, and the semantic range expands, but the number of colors remains unchanged at 4. This is because the 3rd line does not introduce a new semantic range outside of the existing ones. Even with 4 or more lines, the same principle applies. If a new line parallels an existing one, it doesn't introduce a new color requirement. Otherwise, the number of colors needed can be determined according to specific theorems. So what have we journeyed through today? We've delved into the four-color theorem, a cornerstone of graph theory, and explored it through the lens of existential computation and semantic computation. We've seen how a plane can be considered an existential space, with regions as non-intersecting shapes and colors as distinguishing semantics. We've examined how the analysis of existential semantics and semantic range can determine the minimum number of colors required in given scenarios. We've looked at the cases of no lines, 1 line, 2 lines, 3 lines, and even 4 or more lines. And in each case, we've pinpointed the number of colors needed and explained the semantic relationships between these colors. All this, while emphasizing that differentiation of semantics happens within a specific semantic range, a crucial understanding for interpreting the four-color theorem. In conclusion, by translating the four-color theorem into a problem of existential computation and semantic computation, we've gained clarity, identified the minimum number of colors needed, and opened up new avenues for future research. This perspective not only enhances our understanding of the four-color theorem, but also provides an interesting approach to solving similar problems in graph theory and combinatorics. This, my friends, is the beauty of mathematics, where abstract concepts like XCR and ESCR can breathe life into classical theorems, providing us with fresh insights and exciting new directions.